14,000 feet above the gray chop of the English Channel, on an otherwise unremarkable Tuesday in October of 1943, the war was a problem of geometry and physics. For Oberleutnant Klaus Richter, strapped into the cockpit of his Focke-Wulf FW-190, it was the elegant geometry of a predator. He watched the American fighters lumber into view, a formation of Republic P-47 Thunderbolts, and a familiar, dismissive smirk touched his lips. They were absurd machines, corpulent and graceless, flying milk bottles built around the largest engine the Americans could foolishly bolt to an airframe. His FW-190 was a scalpel, a product of precise, logical engineering, its BMW 801 radial engine a masterpiece of refined power. The Americans, he thought, understood only brute force. They strapped their pilots to locomotives and called them fighters. It was a philosophy of waste, of overwhelming with mass what they lacked in sophistication. Today, his scalpel would bleed one of their iron pigs. For First Lieutenant John McManus, inside the cockpit of one of those very locomotives, the war was a visceral problem of physics. He wasn't so much flying a plane as he was aiming an explosion, a barely contained cataclysm of 2,000 horsepower called the Pratt Whitney R-2800 Double Wasp. The entire 7-ton airframe was a compromise, a delivery system for the gargantuan 18-cylinder engine. The stick in his hand felt less like a flight control and more like the handle on a cage holding a beast. Every inch of throttle he pushed forward was a negotiation with forces that wanted to twist his wings off, the torque trying to wrench the fighter into a permanent, unrecoverable roll. He could feel the deep seismic thrum of the engine through the rudder pedals, through the seat, through the bones of his very spine. It was a sound that promised unlimited power, but also whispered of a spectacular mechanical self-destruction. Richter saw his opening. The trailing American fighter, number 774, was slow to respond. He rolled his Focke-Wulf onto its wingtip, the aircraft responding to his inputs with the immediacy of a nerve ending, and dove. McManus saw the flash of the yellow-nosed German fighter arcing down towards his tail and reacted on pure instinct. He jammed the stick hard left and stomped on the rudder, throwing the Thunderbolt into a brutal, high-G defensive brake. The immense force crushed him down into his seat, the world outside the canopy compressing into a gray, featureless blur. For a single, fleeting second, the maneuver worked. But he was asking too much of the machine. He was demanding that the raw, explosive power of the Double Wasp engine be translated in an instant through a set of 3 13-foot duralumin propeller blades, each spinning at over 2,500 revolutions per minute. The failure was not a bang, but a single, sharp, crystalline crack that was felt more than it was heard. It was the sound of a metal's atomic bonds surrendering. Instantly, the thrumming vibration of controlled power became a world-ending violence. The loss of a single 10-foot section from propeller blade number 3 created an imbalance so catastrophic that it was as if a blacksmith were swinging a sledgehammer against the crankshaft 40 times a second. The instrument panel disintegrated into a shower of glass and wire. The engine, with a final shrieking groan of tortured steel, tore itself free from its mounting bolts, ripping through the cowling and cartwheeling into the sky, a blazing comet of oil and fire. The Thunderbolt, its nose suddenly gone, was transformed from a fighter plane into 7 tons of burning debris. The fall was a chaotic, sickening tumble through the freezing air. McManus, fighting the G-forces and the sheer shock, jettisoned the canopy, unclipped his harness, and threw himself out into the deafening silence of the void. His fall was not the result of an enemy's bullet or a pilot's error. First Lieutenant John McManus was a casualty of mathematics. He was a victim of harmonic resonance and catastrophic metal fatigue. The propeller blade that had failed was not merely a fan, it was one of the most complex and highly stressed components in the entire Allied war machine, an exquisitely shaped airfoil tasked with converting the raw, thermal violence of combustion into aerodynamic thrust. and the engines of 1943 were now producing levels of torque and vibration that were pushing the known science of metallurgy past its breaking point. The stress, measured in tens of thousands of pounds per square inch, was finding microscopic imperfections in the forged aluminum alloy, worrying at them, propagating cracks at the speed of sound until the material could no longer sustain the load. This was not a singular random accident. It was a symptom of a vast industrial schism. The war in the air had become a conflict between two opposing philosophies of creation. Germany, starved of resources, pursued the perfect blade, a flawless piece of engineering crafted slowly and meticulously from scarce alloys by master technicians. It was the pursuit of the ideal. America, a continent-wide factory awash in raw materials, pursued the adequate blade, churning them out by the tens of thousands, accepting a certain rate of failure as a simple cost of doing business on an unimaginable scale. The question was no longer who could design the ultimate weapon in a laboratory, but whose industrial system could absorb the brutal, iterative lessons of failure and translate them into victory. The answer to the problem of a single propeller blade failing over the English Channel was not found in a wind tunnel or a laboratory. It was being forged 24 hours a day, 365 days a year, in a sprawling, deafening inferno of a factory in Caldwell, New Jersey. The Curtiss-Wright propeller plant was not a building. It was a self-contained industrial ecosystem, a city-state dedicated to a single purpose, spread over acres of American soil under a permanent haze of smoke and steam. Inside, under the stark glare of thousands of fluorescent lights that banished the very concept of night, the air was a physical presence, thick with the metallic tang of cutting fluid and the low-frequency thunder of drop forges that shook the concrete floor with a relentless, metronomic rhythm. This was not the elegant, precise world of aeronautical design. This was the brutal, violent business of production, an avalanche of steel and aluminum, a war being won not by pilots, but by the sheer, overwhelming mathematics of industrial capacity. In the year before the war, the entire American aircraft industry had produced fewer than 3,000 military planes. Now, this single facility was shipping more than that number of propellers every month, a river of perfectly machined metal flowing out to airfields across the globe. Eleanor May Schmidt was a single anonymous molecule in that river. A young woman from a quiet farming town in rural Pennsylvania, she had, 6 months prior, known only the cycles of the seasons and the smell of turned earth. Now her world was measured by the shriek of a factory whistle and the roar of a furnace. She was not an engineer. She held no degree in metallurgy. She was a line worker, one of millions of women who had traded their aprons for overalls, their kitchens for the factory floor. Her station, one of dozens in a long, cavernous hall, was a heat treatment furnace. Her job was specific, repetitive, and governed by a rigid set of instructions posted on the wall. She would take a rough-forged aluminum propeller billet, a dull gray object that vaguely resembled its final form, and using a long set of tongs, place it into the furnace, which was held at a precise, unwavering temperature. She would set a timer. She would wait. When the bell rang, she would remove the glowing billet and plunge it into a quenching tank of cold water, where it would erupt in a furious hiss of steam. She was one small human gear in a vast and intricate machine, performing a single task whose larger significance was an abstraction, a number on a production quota board. She was a living embodiment of the American strategy, to deconstruct a complex engineering problem into a series of simple, repeatable steps that could be executed flawlessly, endlessly, by a semi-skilled workforce. The life of a single propeller blade began in violence. A red-hot cylindrical billet of aluminum alloy was placed under a multi-ton trip hammer that descended with a deafening, earth-shaking crash, forcing the metal into the rough shape of a blade in a series of brutal, percussive blows. From there, it went to Eleanor's station for the crucial T6 temper. The heat treatment process was the alchemy at the heart of the operation. Soaking the forged billet at a specific temperature for a precise duration realigned its crystalline grain structure, and the sudden, violent quench locked that structure in place, imparting the immense strength and hardness the material needed to withstand the forces of flight. After quenching, the now hardened blade moved down the line to the machine shops, where computer-guided lathes and mills, tended by other women just like Eleanor, would shave away fractions of a millimeter of metal, refining the rough forging into a graceful, complex airfoil. Every curve was calculated, every angle precise. The final step was an X-ray inspection in a lead-lined room, a silent, penetrating search for any internal cracks or voids, any microscopic flaw that could, at 20,000 feet, blossom into catastrophic failure. The entire process, from ingot to inspection, was a testament to rigidity, a chain of command in which specifications created by engineers Eleanor would never meet were translated into physical reality by her hands. It was a system designed to be foolproof, to eliminate the vagaries of human error and produce 1,000 identical, perfect blades a day. And it was within the unyielding perfection of that very system that the seed of a revolution was about to be unintentionally sown. Thousands of miles away from the industrial thunder of New Jersey, in a hushed, sterile laboratory in Augsburg, Germany, the same problem was being approached not with brute force, but with the quiet intensity of religious devotion. The Messerschmitt Research and Development Facility was a sanctuary of the mind, a place of clinical silence where the war was reduced to a series of elegant, solvable equations. Here, there was no smell of oil or hot metal, only the faint, clean scent of ozone from electrical equipment and the whisper of air through ventilation ducts. The floors were polished concrete, the light was the cold, unwavering glare of the laboratory, and the only sounds were the precise, delicate clicks of calipers and the dry scratch of a graphite pencil on vellum. This was the intellectual heart of the German war machine, and its high priest was a brilliant, ascetic man named Dr. Ingenieur Friedrich Kessler. Kessler was a metallurgist, but he considered himself an artist, and his medium was the crystalline structure of alloys. His office was less a workspace and more a testament to his obsession. The walls were covered not with maps or charts, but with vast, intricate diagrams depicting the hexagonal, close-packed, and face-centered cubic lattices of aluminum alloys. Polished cross-sections of propeller blades, etched in acid to reveal their grain structure, rested under glass bell jars like precious relics. He was the absolute antithesis of the American system, a single, towering intellect against a continent of factory workers. He had seen the intelligence photographs of the captured American P-47s, and they filled him with a cold, academic contempt. To him, they were not merely inefficient, they were an offense against the laws of physics, a testament to a philosophy of grotesque excess. They solved the problem of power by building a bigger engine, the problem of durability by adding more metal. It was, he mused while examining a micrograph, industrial butchery, not engineering. They thought victory could be achieved with a bigger hammer. His own work was the pursuit of a different kind of victory, a victory of the intellect. He sought the perfect alignment of grains, a metallurgical purity that would yield the theoretical maximum strength-to-weight ratio. He was not merely building a propeller, he was coaxing a material toward its state of ultimate perfection. The process was an art form, a delicate ballet of precise heating, controlled cooling, and trace additions of exotic elements. But Kessler's genius was forged in the crucible of scarcity. The elegant equation on his blackboard was beautiful, but it was also damning. It called for nickel to impart toughness, for manganese to increase strength, for chromium to resist the relentless corrosion of the elements. And the Third Reich was bleeding these vital materials. Every gram of chromium had to be weighed against its use in tank armor, every kilogram of nickel against its need in submarine hulls. He could not afford waste, An improperly mixed alloy, a billet held in the furnace a minute too long, was not an acceptable loss. It was a strategic failure. His process was therefore slow, unforgiving, and exquisitely precise. Each blade was a masterpiece, born of genius and desperation. But his laboratory, running at peak efficiency, could perhaps guide the production of 24 such masterpieces in a day. Each one was a testament to German ingenuity, a flawless, lightweight marvel of material science. And each one was another nail in the coffin of the German war effort, because while he was perfecting the one, the Americans were shipping the 10,000. He was composing a perfect symphony for a world that was being deafened by the roar of an avalanche. The intellectual purity of Dr. Ingenieur Kessler's laboratory in Augsburg was a meaningless abstraction to the men of the 398th Bombardment Group, suspended 5 miles above a frozen German landscape. For them, the war was a simple, brutal reality of noise, cold, and vibration. Inside the unheated aluminum fuselage of the B-17 Flying Fortress, nicknamed Vicious Virgin, the world had been reduced to a single overwhelming sensory input, the constant, deafening, soul-shaking roar of 4 Wright R-1820 Cyclone engines. It was not a sound one simply heard. It was a physical force that pressed in from all sides, a seismic, ceaseless concussion that vibrated through the thin metal skin, up through the floor, and into the very marrow of the 10 men inside. Each man was an island in a sea of cacophony, communication possible only through the crackle of the intercom. The pilot, Captain Frank Gallo, and his co-pilot kept their hands in constant subtle motion, fighting the controls, feeling for the slightest change in the texture of the vibration, listening for any discordant note in the 4-part harmony of destruction that was propelling them toward the ball-bearing factories of Schweinfurt. Every man in that crew, from the pilots in the cockpit to the tail gunner isolated in his plexiglass cage, understood that their lives were utterly dependent on the mechanical integrity of 48 pistons, 4 crankshafts, and 12 spinning propeller blades. An engine failure was not an inconvenience. It was a potential death sentence. The flight engineer, Staff Sergeant Mike Stanislaw, never took his eyes off the bank of engine gauges, his body a human seismograph tuned to the health of his power plants. He knew that the loss of a single propeller blade, a component forged and finished by someone he would never meet in a factory he would never see, would unleash a force of unimaginable violence. The sudden, catastrophic imbalance would act like a celestial hammer, striking the wing with a force that could, in seconds, tear the entire engine from its nacelle and send the 30-ton bomber into an unrecoverable, spinning dive. They were flying a machine that was constantly threatening to tear itself apart, a fragile vessel held together by the quality control of 1,000 strangers. These were the hammers from heaven, an armada of over 700 heavy bombers arrayed in a vast geometric procession across the winter sky, each one a carrier of 10,000 pounds of high explosives and 10 human lives. Below them lay the target, defended by a curtain of flak and the promise of enemy fighters. But the greatest danger the crew of the Vicious Virgin faced that day was not the elegant lethality of a German Focke-Wulf or the random chance of an 88mm shell. The most insidious threat was a simple, invisible crack, a microscopic flaw in the grain of a propeller blade, a silent weakness that had passed every inspection and was now being subjected to stresses its designers had never fully anticipated. The crews knew this not through engineering reports, but through the grim empirical evidence of empty bunks back at the airfield. The official ledgers of the 8th Air Force recorded the terrible calculus of the air war in cold, dispassionate columns. During the brutal raids of the preceding month, a staggering number of aircraft listed as lost to enemy action had, in fact, never made it to the target. Of the 60 bombers lost in a single raid, 17 were later confirmed to have aborted or gone down due to mechanical failure, the vast majority of those being catastrophic engine and propeller malfunctions. It was a secret and relentless attrition, a war against their own machinery that was costing them more lives than the Luftwaffe. The abstract problem of metallurgy, the complex mathematics of stress and harmonic resonance, had a simple human name. It was the name of the man who didn't come home for dinner. It was the urgent, unspoken question hanging in the air of the factory in Caldwell, New Jersey, 3,000 miles away. The air in the Caldwell factory was different on the late shift, thicker somehow. After 10 relentless hours of work, the atmosphere seemed to gain a physical weight, saturated with the smells of hot metal, ozone, and the ever-present cloying scent of industrial cutting fluid. Under the unforgiving glare of the long fluorescent tubes, the world for Eleanor May Schmidt had shrunk to the glowing orange maw of the heat treatment furnace, the heft of the steel tongs in her hands, and the insistent, nagging ache in the small of her back. It was Tuesday, just past midnight, and the initial patriotic fervor that had carried her from Pennsylvania had long since been worn down into a state of dull, aching fatigue. Her movements were automatic now, a rhythm learned by muscle and bone, divorced from conscious thought. She was a human metronome, keeping time with the ceaseless pulse of the factory around her. The distraction, when it came, was so trivial as to be almost imperceptible. Her line supervisor, a harried man with permanently shadowed eyes, paused by her station. He didn't speak to her, but to the operator next to her, a loud, sharp question about a misaligned pallet that cut through the background roar for a mere moment. Eleanor's head turned reflexively toward the sound. In that same instant, a heavy steel bin of forged billets was dropped by a crane at the far end of the bay, the impact a sudden concussive boom that sent a tremor through the concrete floor. For perhaps 5 seconds, her attention was diverted. It was a momentary ripple in the deep, monotonous ocean of her shift, a thoughtless, instinctual reaction to a change in her environment. When her eyes returned to her workstation, her mind was already back in the rhythm. She pulled the next billet, a heavy, inert piece of shaped aluminum, and slid it into the furnace, its dull gray surface instantly beginning to shimmer and glow in the 500°C heat. She reached for the timer, her mind a step ahead, already anticipating the bell and the subsequent violent hiss of the quenching tank. But in that brief 5-second lapse, a critical connection had been broken. Her hand, acting on the memory of 1,000 identical cycles, set the timer. Her brain, however, failed to register that the previous cycle's bell had already rung and been silenced during the distraction. The new billet was now soaking in the intense, transformative heat on a timer that was already partway through its countdown. The specification, printed in stark black letters on a metal plate bolted to the furnace, was absolute, the product of countless hours of engineering calculation, a precise duration at a precise temperature. No more, no less. Unseen, unheard, the billet remained in the furnace for an additional 3 minutes. It was a tiny, insignificant deviation in a multi-hour process, a statistical ghost, a rounding error in a day that produced over 1,000 identical components. Unbeknownst to her or to anyone, those 180 extra seconds were performing a forbidden alchemy. Deep within the metal, the carefully engineered crystalline grain structure was being subtly corrupted. The prolonged heat was relaxing the atomic bonds, allowing the grains of the alloy to grow, to become coarser, fundamentally altering the material's most basic properties in a way the engineers had meticulously designed the process to prevent. When the bell finally rang, Eleanor removed the billet, now glowing with an almost liquid incandescence, and plunged it into the quenching tank. The resulting explosion of steam was identical to every other. The process on the surface was complete. The billet cooled, hardened, and moved down the line. It was stamped by a pneumatic press, receiving its unique identity, a serial number, a long string of digits and letters that linked it not to a person or a moment of distraction, but to a specific date and production batch. It continued its journey, passing under the unblinking eye of the X-ray machine. Its surface hardness was tested and found to be within tolerance. Its dimensions were checked by precision calipers and found to be perfect. The deeper structural change, the ghost in its grains, was entirely invisible to the tools of inspection. It was a flawed masterpiece, a perfect imitation of its brethren. The mistake, born of a moment's fatigue and a trivial distraction, had been officially sanctioned, serialized, and absorbed into the immense, anonymous avalanche of steel. It was just one more blade among thousands, its profound secret locked deep within its altered heart, waiting for its appointment with destiny on a rain-swept airfield in England. The cold, damp air of an English evening was settling over Royal Air Force Snetterton Heath, carrying with it the familiar, pervasive smells of high-octane aviation fuel and wet soil. For the ground crews of the 96th Fighter Squadron, the end of the day brought not rest, but the beginning of the long, methodical ritual of repair and maintenance. Under the harsh, temporary floodlights that cast long, dancing shadows across the PSP hardstands, men with grease-stained hands and a bone-deep weariness moved like ghosts, tending to the wounds of the great iron birds they served. It was in this environment of routine exhaustion that the anomaly first revealed itself, not with a bang, but with the dull, metallic clang of a tired pilot making a simple mistake. Second Lieutenant Billy Croker, numb after 8 hours in the air, misjudged his turn while taxiing, and the tip of his P-47's propeller clipped a 55-gallon fuel drum that had been carelessly left near the taxiway. The impact was low speed, almost gentle, but in the world of high-performance aircraft, it was an act of profound mechanical violence. Master Sergeant Sully Sullivan heard the sound and felt it in his teeth. He didn't even need to look up. It was the sound of a long night and a mountain of paperwork. He was the crew chief, a grizzled veteran of 1,000 such minor disasters, and he knew exactly what he would find. He grabbed a flashlight and walked toward Croker's Thunderbolt, his boots crunching on the gravel, already mentally filling out the forms for a full propeller and engine replacement. He'd seen it 100 times before. The Curtiss electric propellers were marvels of engineering, but their duralumin blades, hardened to a state of extreme rigidity through the T6 temper process, were fundamentally brittle. When they struck an object, they did not bend. They shattered. They failed like glass, snapping off in a clean, crystalline fracture that sent shrapnel tearing through the engine cowling and often shock-loading the crankshaft into a warped, useless piece of steel. Sully knelt beside the massive Pratt Whitney engine, shining his light on the damaged blade, his mind already composing the scolding he would give the offending drum mover. And then he stopped. The words died in his throat. What he was seeing was impossible. The propeller blade had not shattered. It had not snapped. It had bent. The last 18 inches of the thick airfoil-shaped aluminum were twisted back at a grotesque 45-degree angle, the metal deformed in a smooth, plastic curve as if it had been made of soft lead. He ran a gloved hand over the impact point. There were no fracture lines, no crystalline shears. The material had absorbed the kinetic energy of the impact by deforming, not by breaking. It was an aberration, a violation of the known laws of his mechanical universe. For 15 years, Sully had worked on these machines, and in all that time he had learned one absolute immutable truth. Hardened aluminum was brittle. This was something else. He stood up slowly, a strange feeling creeping over him, a mixture of confusion and profound electric curiosity. Standard operating procedure was clear. A prop strike of any kind meant the entire assembly was condemned, scrapped, melted down, and returned to the great industrial cycle. But this was not a standard prop strike. This was an anomaly, a ghost in the machine that whispered of something new. He looked at the base of the blade, his flashlight beam finding the small stamped plate riveted to the hub. It was covered in grease, but the serial number was clear. On his clipboard, instead of checking the box for scrap, Sully wrote in block letters, "Structural anomaly, unusual failure mode, recommend engineering analysis." He knew the report would likely be lost in the vast bureaucracy of the air war, but it was a chance he had to take. The blade, with the unknowing signature of Eleanor, May Schmidt's 3-minute error encoded in its very molecular structure, was carefully unbolted from the hub. It was tagged, crated, and 2 days later loaded into the belly of a C-47 Skytrain bound for the United States. Its destination was no longer the scrapyard, but the propulsion laboratory at Wright Field, Ohio, where the men who wrote the laws of metallurgy would be forced to confront a mystery forged in a moment of human distraction 3,000 miles away. At Wright Field, Ohio, the propeller blade arrived not as a piece of damaged equipment, but as a scientific artifact, an object of intense and skeptical curiosity. Here, in the pristine, climate-controlled laboratories of the Army Air Force's Primary Research and Development Center, the brutal realities of combat and the chaotic thunder of the factory floor were filtered out, leaving only the clean, cold language of data. The bent blade, with its impossible curve, was handed over to the metallurgists, the quiet, methodical men in white coats whose job it was to understand the fundamental truths of the materials from which the war was being built. They approached it not with wrenches, but with diamond-toothed saws and electron microscopes. The first step was vivisection. The blade was carefully cut into sections, its graceful airfoil shape destroyed in the service of a deeper understanding. Polished cross-sections were mounted in resin and placed under powerful microscopes. What the engineers saw on the viewing screens was immediate and deeply troubling. The grain structure of the aluminum alloy was fundamentally wrong. The specifications called for a fine, tightly packed crystalline matrix, a structure that gave the material its immense hardness and tensile strength. But this blade's internal architecture was coarse, almost porous by comparison, with large, elongated grains. It was the metallurgical equivalent of flawed masonry. Next came the Rockwell hardness tests, where a diamond-tipped cone was pressed into the metal's surface. The results confirmed their suspicions. The blade was softer than specified, failing to meet the minimum hardness required for service. Finally, samples were placed into tensile testing machines, which would pull them apart with immense force. The data that came back was the final baffling piece of the puzzle. The material's ultimate tensile strength, its ability to resist being pulled apart, was significantly lower than that of a standard, good propeller blade. And yet its ductility, its ability to bend and deform without fracturing, and its overall toughness, the measure of its ability to absorb energy, were dramatically, impossibly higher. The numbers on their clipboards presented the engineers with a paradox that bordered on heresy. By every established metric, every rule written in their textbooks, and every specification handed down from on high, this was a defective, substandard, and unequivocally bad blade. It was weaker, it was softer, and its internal structure was flawed. Yet this objectively inferior piece of metal had survived an impact that would have shattered a technically perfect one. It had failed in a way that was profoundly, strategically superior. The system had produced an anomaly that was better than its own intended product. The revelation was stark and undeniable. Their definition of perfection was wrong. Forced to abandon their assumptions, the engineers became detectives. Their only clue was the string of digits stamped onto the blade's hub. That serial number became their Rosetta Stone, a key that allowed them to unlock the component's entire manufacturing history. Cables were sent. Records were requisitioned. They traced the metal back to a specific ingot of aluminum poured at an Alcoa plant in Tennessee. They followed that ingot to a forging press at the Curtiss-Wright facility in New Jersey. They cross-referenced the forging batch with machining logs, narrowing the time frame down to a single week in late 1943. The paper trail led them deeper and deeper into the industrial machine, finally terminating at a specific workstation in the heat treatment hall. Furnace station number 4, late shift. The work logs for that station on that specific night provided them with a name: Eleanor May Schmidt. The engineers in their quiet Ohio laboratory looked at the name of this unknown woman from Pennsylvania, and the final piece of the puzzle clicked into place. They were not looking for a saboteur or a genius. They were looking for a simple human variable. Running their calculations and consulting their heat treatment charts, they realized there was only one possible way to create the coarse-grained, highly ductile structure they had discovered. The blade had to have been improperly heat-treated. It had to have been left in the furnace for too long at too high a temperature, a process they knew as solution heat treatment. It was not an intentional act of metallurgical brilliance. It was a mistake. A simple, human error born of fatigue or distraction on a factory floor 3,000 miles away had inadvertently created a material that was more resilient, more damage-tolerant, and ultimately more lethal than anything their rigorous by-the-book science had ever conceived. The conclusion reached in the quiet, sterile laboratories of Wright Field was a seismic event, a fundamental challenge to the very scripture of modern engineering. The meticulous specifications, the product of 100,000 man-hours of calculation and testing, were not just incomplete, they were wrong. The system, in its vast churning and imperfect operation, had stumbled upon a truth that rigorous by-the-book science had completely missed. It was a profound and unsettling paradigm shift. Victory, it seemed, was not to be found in the pursuit of theoretical perfection, but in a system so massive that it could afford to make mistakes, learn from them, and then industrialize the lesson at a terrifying scale. The bad blade was superior. The error was the solution. The ghost in the machine was now in command. The first step was to capture lightning in a bottle, to transform a random human accident into a repeatable scientific process. Back in the labs, engineers began the work of deliberately replicating Eleanor Schmidt's mistake. Using furnaces identical to the one in New Jersey, they subjected dozens of forged billets to a battery of tests, meticulously documenting every variable. They soaked the metal for an extra minute, then 2, then 3, then 4, precisely calibrating the relationship between time, temperature, and the resulting crystalline structure. They discovered the perfect window, the sweet spot where the alloy traded a small acceptable amount of tensile strength for a massive game-changing increase in ductility and fracture toughness. The 3-minute error, the momentary lapse on the Caldwell factory floor, was no longer an error. It was codified, canonized, and given a new official designation, specification number 227B. What followed was an act of industrial whiplash, the redirection of a continental-sized machine. From the highest levels of the War Department in Washington, D.C., urgent communiques began to flow. Teletype machines in factories from New Jersey to California chattered to life, spitting out new production orders that rendered all previous instructions obsolete. Engineering departments worked around the clock, drafting new manuals and blueprints. On the factory floors, the physical change was swift and absolute. The old specification plates were unbolted from the heat treatment furnaces and thrown onto scrap heaps. New plates bearing the gospel of specification 227B were bolted in their place. An action that would have resulted in a reprimand 1 week was the mandated critical procedure the next. The immense, seemingly unstoppable inertia of American mass production, a force that had been charging in one direction for years, was halted, pivoted, and set upon a new course. The result was a torrent of steel, unlike anything the world had ever seen. The new blades, designated with the model number C532S, began to flow into the supply chain. The pace was staggering. Within the first 30 days, over 50,000 of the new, more resilient propellers were produced. Within 3 months, that number had climbed to 200,000. The flawed blades were purged from the system, and a new, stronger weapon, born from an anonymous woman's fatigue, was being bolted to the nose of every new fighter and bomber rolling off the assembly lines. Back in Caldwell, New Jersey, Eleanor May Schmidt stood at her station, her world unchanged. A new specification plate was on her furnace. The timer was to be set for 3 minutes longer. She did not know why. It was not her job to know why. It was her job to pull the lever to set the dial and to meet the quota. Without a single thought of the consequence, she continued her work, flawlessly executing the new rules she had unknowingly written, a silent, unknowing architect of an impending victory. By the autumn of 1944, the sky over Germany had changed. For Oberleutnant Klaus Richter, it was no longer his sanctuary, no longer the vast open arena where his superior skill and superior machine could prowl with impunity. It had become a crowded, hostile space, choked with the sheer, overwhelming mass of the enemy. The sky itself seemed to have been replaced by a ceiling of aluminum, a permanent, glittering overcast of American bombers, and worse, their endless swarms of escort fighters. They were still brutish machines, but they were different now. They flew with a new feral aggression. Their pilots pushed them into screaming high-speed dives that previously would have shredded their propellers. And their engines held a steady, unwavering roar, a confident note of mechanical reliability that grated on Richter's nerves. He witnessed it himself on a Tuesday in November during a desperate high-altitude interception near Leipzig. A burst of flak, meant for a bomber, blossomed near a P-51 Mustang. Richter saw the flash and the puff of black smoke, saw the American fighter shudder as shrapnel tore into it. He watched, waiting for the inevitable, satisfying conclusion. The thrown propeller blade, the engine tearing itself from its mounts, the blossoming fireball. But it never came. Instead, the Mustang's propeller, though clearly damaged and vibrating violently, remained intact. One blade was visibly bent, a grotesque caricature of its intended shape, yet it held. The American plane, trailing smoke and glycol, broke formation and began a long, painful, but controlled descent westward. It was limping, but it was alive. It was going home. That single, impossible image of a blade that bent instead of breaking was more terrifying to Richter than any enemy gun sight. The Americans' crude, disposable machines had somehow learned to endure. That same afternoon, the sound of the Allied bomber streams rumbling miles overhead reached the laboratory of Dr. Ingenieur Friedrich Kessler in Augsburg, a low, persistent tremor that vibrated through the concrete floor and rattled the glass beakers on his workbench. He tried to ignore it, to focus on the elegant, crystalline perfection of the single propeller blade mounted in his testing jig. He was on the verge of another breakthrough, a new tempering process that promised a 2% increase in tensile strength. But his breakthrough was a ghost, a theoretical victory in a war that had become brutally, hopelessly physical. The rumble from the sky was the sound of his irrelevance. The rare earth alloys his equations demanded, the nickel, the chromium, the vanadium, were now just memories, requisitioned for panzer divisions that no longer existed and jet engine prototypes that would never fly. He was forced to work with alloys contaminated with manganese, compromising the purity of his grain structure. His quest for the perfect blade had become an academic exercise, the work of an artist in a burning museum. While he spent a week coaxing a single, flawless masterpiece into existence, the Americans, with their flawed, soft but resilient propellers, were dropping thousands of tons of bombs on the very factories that were supposed to produce his designs. His perfection had been rendered meaningless by their overwhelming, battle-hardened adequacy. The true impact of Eleanor Schmidt's 3-minute error was not measured in a laboratory, but in the cold, hard calculus of the air war. The stronger, more ductile blades transformed the operational capabilities of the entire 8th and 9th Air Forces. Pilots, freed from the fear of catastrophic blade failure, could now employ more aggressive tactics. They could push their superchargers to their absolute limits, dive at speeds that flirted with the sound barrier, and pulled G-forces that pressed them to the edge of consciousness. The operational readiness rates of every fighter and bomber group in the European theater ticked upwards. The number of non-combat losses due to engine failure, the quiet, persistent drain on men and machines, plummeted by a staggering 35%. That small, accidental change, multiplied by the relentless logic of industrial scale, had become a tangible strategic weapon. It meant more planes in the air for every raid, more bombs on target for every mission, and most importantly, more pilots returning home from the fire-swept skies over the crumbling Reich. The mathematics of attrition, once a grim and uncertain equation, had been fundamentally, decisively altered in America's favor. The war ended, and the great industrial machine, having consumed continents and remade the map of the world, slowed its frantic rhythm. In a quiet corner of rural Pennsylvania, the air no longer carried the distant rumble of bombers on training flights, but only the familiar sounds of wind in the trees and the lowing of cattle. Here, Eleanor May Schmidt had returned. The overalls were packed away, the smell of cutting fluid washed from her hands, the deafening 24-hour-a-day roar of the Caldwell factory a fading, dreamlike memory. She lived a simple life, married a local man, and never once spoke of her time building the weapons of war. She was a footnote in a story she did not know she had written, an unknowing architect of a victory whose scale she could never comprehend. Her contribution was not a single act of heroism, but a moment of anonymous human imperfection, absorbed and amplified by a system so vast it rendered the individual irrelevant. Her quiet peace was the dividend of a brutal investment, paid for by men like First Lieutenant John McManus, who fell from the sky in a hail of his own. Disintegrating engine. The solution, born from her simple mistake, came too late for him, and for the hundreds of other airmen who were casualties not of enemy fire, but of the unforgiving physics of metal fatigue. Their names are etched onto memorials, silent testaments to the brutal iterative process of wartime innovation, where every engineering lesson is paid for in blood, and the right answer is often discovered only after an exhaustive exploration of all the wrong ones. It is the unapologetic, pitiless calculus of industrial attrition, a war won not just by soldiers, but by the relentless, unsentimental logic of the production line. The final verdict was not written in the memoirs of generals, but in the cold, dispassionate ledgers of the United States Army Air Forces. The statistical reveal is absolute. Following the introduction of the new blade specification in early 1944, the rate of in-flight catastrophic propeller failures across the entire European theater of operations fell by a staggering 35%. This single change directly correlated to a 15% increase in the operational readiness rate for the heavy bombers of the 8th Air Force during the critical final year of the war. Conservative estimates by the Air Technical Service Command concluded that the stronger, more resilient blade saved over 150 B-17 and B-24 bombers from mechanical destruction, and with them, the lives of an estimated 1,500 crewmen. The ultimate victory was not simply one of arms, but of production. It was a victory of a system that could turn a simple human mistake in a New Jersey factory into an unbreakable weapon wielded a mile above the rubble of the Third Reich. The true architect of that stronger propeller blade was not a single engineer, nor the woman who made the mistake, but the entire, chaotic, relentless, and ultimately triumphant force of American industry itself.